Welcome everybody. Now we start to learn how to solve second order constant coefficient. It's a mouthful. Second order constant coefficient linear homogeneous equations. Okay. All right. Like I said, it's a bunch to say. Okay. So now what we want to do is figure out a way to solve these in general. And then that's going to lead us to looking at three special cases, as we'll see. So first of all, let's write down a second order constant coefficient linear homogeneous equation. Okay. So that is an equation of the form AY double prime plus BY prime plus CY equals 0. So A, B, and C are real numbers. This is a little blurry, so let me try to get it to straighten up. Okay. And A is not equal to 0. Otherwise, it's not second order. Okay. So we want to solve this. And how do we do that? Well, barring anything else, we better make a good guess. So let's make a guess at a solution and hope for the best, that our solution is like an exponential. Let's say e to the lambda x. Now, we don't know that that's correct at this point. We have to just try and see if that works. So let's see. If you do that, then y prime is equal to lambda e to the lambda x, and y double prime is lambda squared e to the lambda x, just by regular old differentiation from calculus 1. So now we put that into our equation. We put that into our equation, and it says that lambda squared times a e to the lambda x plus b lambda e to the lambda x plus c e to the lambda x equals 0. And notice there's a common factor of e to the lambda x. So let me take that out. Okay. And now I can divide by e to the lambda x, because e to the lambda any, or e to the anything, is never equal to 0. So we can divide by it and get a e to the lambda squared, lambda squared plus b lambda plus c equals 0. So notice we went from an ordinary differential equation. This is the one we want to solve. So let me call that asterisk. And now we've reduced that to solving this quadratic equation. In other words, e to the lambda x will be a solution if lambda satisfies this. So lambda is lambda has to be a solution of the quadratic equation. Well, we know what happens with the quadratic equation. You have three cases, right? You have three cases of a possible solution. One is that you have two real distinct roots. Let's say lambda 1 and lambda 2. Okay, so they're distinct, so they're not equal. You have two complex conjugate roots. That's another possibility. So lambda is equal to alpha plus or minus I times beta for alpha and beta real numbers. Okay. And the other possibility is you have one double root. That is, lambda is equal to b over a. And I'll go over how you get each one of those, but that's elementary high school algebra. Okay, so how do you solve the quadratic formula so that you can see that? Just remember, what is the solution of the quadratic equation? By the quadratic formula. So by the quadratic formula, we know that lambda is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so that's what you remember from high school, hopefully algebra 1. Okay, and now you see that each one of those cases above corresponds to a different case for the discriminant. So if the discriminant is greater than 0, that is b squared minus 4ac is greater than 0, that corresponds to case 1. Okay. And if b squared minus 4ac is negative, that corresponds to case 2, because then you have a negative number underneath the square root sign, so you get complex roots. Okay. And you can see that, you can see exactly what alpha is. Alpha is minus b over 2a. So in this case, alpha is minus b over 2a, and beta is the square root of b, well, it's actually 4ac minus b squared, because you want the net, well, that's not very readable, over 2a, the square root of this, because this is the positive number. That's 4ac minus b squared over 2a, because b squared minus 4ac is negative in this case, so to make it positive, and then the I takes care of the square root of the minus 1. Okay, so that's how we get that. And then the double root is when b squared minus 4ac is actually 0. Okay, and that says where minus b is equal to, oops, this is minus b over 2a. Wrote that wrong. That's the problem with trying to memorize things. Little bit of memory slip and you remember the answer incorrectly. It's better just to remember how to get it and work things out. Okay, so we have 3 cases we're going to have to study for roots of this equation. We need to study when we get 2 real distinct roots, 2 complex conjugate roots, and 1 double root for each lambda. And then how do we build the general solution to this equation? Well, before we get to that, we have to even figure out, what do we mean by a general solution to this equation? So that, remember, our equation is y double prime, ay double prime, plus by prime plus cy equals 0. And so we need to get a general solution to this equation. And we know that by the principle of superposition, we know that if y1 and y2 are solutions, we call this equation asterisk. Asterisk. Then so is C1 Y1 plus C2 Y2 for C1, C2, any arbitrary real numbers. Okay. And what we'll see in a later section we will show any solution of star can be written in the form y is C1 Y1. And let me remind you that these are functions and the C1 and the C2 are constants. so long as y1 is not a multiple of y2. Now, that's not a very precise way of stating what we're going to say more generally later, but it's enough for right now, that y1 and y2 are genuinely different. One just isn't a multiple of the other. Okay. Later on, we'll get, excuse me, a more general notion that we will be used to, that we'll be able to use to extend to higher order equations. And we'll call that linear dependence and linear independence. But if you only have two functions, one is they're linearly independent as long as one is not a multiple of the other. So that's all we really need for right now. Okay. So we need to find two genuinely different solutions for our equation. And then any solution can be is written as it can be written as a linear combination of those two solutions. Okay, so in this video, we're going to focus on case 1. And that is where the equation, which I call double star, has two real distinct roots. Let's call them lambda 1 and lambda 2. Okay, so lambda 1 is minus b plus the square root of b squared minus 4ac all over 2a. And lambda 2 is similar, but with the minus sign in front of the square root term. Okay. And by the way, this equation has a name, what I call double star before. It's called the characteristic equation. Okay. So when the characteristic equation has two real distinct roots, that happens when the discriminant's positive. Okay, that is the b squared minus 4ac, remember the term discriminant. Okay, and so when this case happens, then one solution is e to the lambda 1x, another solution is e to the lambda 2x, and as long as lambda 1 and lambda 2 are different, which we are assuming in this case, then neither one of these is a multiple of the other. So, and y1 is not a constant times y2 when lambda 1 and lambda 2 are different. Okay, so the general solution in this case is y of x is c1e to the lambda 1x plus c2e to the lambda 2x. Okay, and that's it. That's the general solution. Okay, so let's look at an example. Okay, let's look at an example. So suppose we take y double prime minus y prime minus 12y equals 0. And we are asked to find the general solution. Okay. All right. So I'll make that the first part of the question. We'll have a second question in a second. All right. So if we ask to find the general solution, what do we do? By the calculations we just did, we remember that basically we're looking for a solution of the form y(e) to the lambda x. And when you go through the calculations, you end up with a characteristic equation where derivatives are replaced by powers of lambda. So the second derivative becomes the second power of lambda. Then you put the same sign, then the first derivative becomes the first power of lambda, and the 0th derivative is the 0th power of lambda. Okay, so that's our characteristic equation for this problem, for this example. So now, how do you solve this equation? You can use the quadratic formula, but if you can factor, that's easier. And you will generally find that it's easier to make a mistake doing the quadratic formula, just doing the arithmetic, than factoring. And factoring is faster, or should be faster. So if you look at this one to factor, it factors to y, lambda minus 4, lambda plus 3. Okay. So that means that you get two solutions. One is lambda equals 4. Let me call that lambda 1. And the other is lambda 2 is minus 3. So that's two real distinct roots. So our general solution for this problem is y of x is c1 e to the 4x plus c2 e to the minus 3x. Okay. And it doesn't get any easier in this class than these kinds of problems. Okay. Now that's a second order equation. Notice we have two arbitrary constants. So if you wanted to pin down a precise solution, you would need two pieces of data. So let's suppose in addition, we know that y of 0 equals 1 and y prime of 0 equals 0. I don't know if you can hear in the background my two golden retrievers. They seem very blasé about this lecture, but they're making a little noise in the background. Sorry about that. Okay, so suppose we know that y of 0 is 1 and y prime of 0 is 0. Then we can use these two pieces of data to specify the constants. So we know the general solution. Okay, so here's the question, find the explicit solution or the exact solution to our original differential equation with these two pieces of initial conditions. So this is y that we just found, and we're going to need y prime so we can evaluate it. So y prime is going to be 4c1 e to the 4x minus 3c2 e to the minus 3x. And now we know y of 0 equals 1. But on the other hand, y of 0 from this formula is going to be c1 plus c2. Okay, and we know that y prime of 0 is 0, but y prime at 0 from this formula is 4c1 minus 3c2. So again, we have two equations in two unknowns. Solve it by your favorite algebra method that you learned in high school. Okay, so that this one, I would do this one first. So that will say C1 is 3/4 C2. And now I can plug into this equation. So that will be C1 is 3/4 C2 plus C2. So that's 4/4 and 3/4, that's 7/4. 7/4 C2 is equal to 1, sorry. And so that says 4/7 is equal to C2. And now plugging over here, that says C1 is 3/4 times 4/7, so it's 3/7. Okay, so our exact solution then is, we look at this one, and now we know what C1 and C2 are. So y of x is 3/7 e to the 4x plus 4/7 e to the minus 3x. Okay, and there's your answer. And you can always check it by differentiating twice, plugging into the equation, plugging in the initial conditions, making sure they work. For example, here you can very quickly see that if you plug in y of 0, you get 3/7 plus 4/7, that's 7/7, that's 1. And y prime at 0 is 4 minus 4 minus 3, I'm sorry, where you have to remember what C1 is. So it's 4 times C1, which is 12 sevenths, minus 3 times C2, which is minus 12 sevenths, and plus, you add them together, you get 0, which is that condition. Okay, so it satisfies the conditions clearly. You could differentiate it and check to make sure that it satisfies the differential equation, but I guarantee you it does. Okay, and that's what you do for the case of the constant coefficient, second order linear homogeneous equations with two real distinct roots. Okay, next lecture we'll look at what goes on when you have two complex conjugate roots. Okay, bye.